right? It's either up or down. So 2. So can you guys think of a matrix, a ket, that's normal? I mean, that's normalized?
0, 1.
Okay, how about, yeah, so how about this? Up equals a 1, 0. And then down is a 0, 1. Are they normalized?
Yes.
Yeah, they're normalized.
Yeah, because they have an actual value.
Yeah. All right. So let's now build a general spin state. So Griffiths uses this notation. He uses a psi, which is a generalized spin state, which he calls a spinner. So how can I build a generalized spin state in this 2D basis?
You need some constant times up plus some constant times down.
How about A times, let's see, I'll go with, so I would say like this, A times up, and then plus B times down. My notation is a little bit different in this section than his. I mean, yeah, so that's what we've got, right? And then you can find, and then how do we interpret the A's and the B's?
Like cross,
A squared is what?
A squared is
And B squared is?
Probability of spin down.
All right, so you'd have to normalize this. All right? So the next step is let's build some operators. Let's build some operators in this space.
What is that saying that broad on the left? The
Well,
bottom?
so what I'm trying to do is this. What I'm trying to do is tie this together with what we've been doing generally all around. Summation over n, Cn psi n. Is that how we're doing here?
Yep.
I didn't see that, but now I guess I do.
Okay, so that's what I was trying to tie together.
So it says X general.
Psi general spin state,
Yes.
he calls a spinner.
All right. Oh, okay. So kind of-
That's actually
That's chi.
the symbol chi.
Chi, yeah.
Don't confuse your chi's and
Oh yeah,
psi's.
like chi squared.
Yeah.
Yeah, thanks.
But like,
Can you
the
cut
one
that out
on the left, that general, side general,
Yeah.
that seems to be able to make like this multitude of diversity with regards to waves, and this only has the 2 states.
Right, it's 2-dimensional. Is it a complete basis set?
Yeah. So
So that's why I draw the
This
connection.
is more specific then.
Yeah.
What we're doing is we're doing a finite dimension space. The finite dimensions are they spin up and spin down, that's it.
Where n is 2, so therefore you have.
Yeah, when you sum over those 2.
Is it
you get A
complete?
and B.
Is it complete?
Yep.
Do those span the space?
Yeah.
I'm done.
But is it still solving the quantum mechanical problem?
Yeah. It's a 2-dimensional space. So I always think of this as if it's like you know the answers. Now you just got to make up the complex abstract vector space to make it work, I guess.
You figured out what it is, now you gotta make up the math to go with it.
Yeah, you kind of know the answers, all right? So I go and I look, and the spins can only be up or down for electrons, so now I'm going to figure out all the other stuff. And then with the other stuff, I can do some calculations that I wouldn't know, right away. I really got to get through this today, yeah.
I just wanted to. So you're gonna figure out on the left, and then figure out like the spin.
Just follow me. No, this is I'm not doing, Mike, this should make complete sense. These are these that we've been doing all along. It's finite.
Yeah.
Right? Those are our basis set. Those are our normalized basis set and function space. Well, it's not really function space, it's an abstract.
Spin space.
This is an abstract space. There's no function here.
Spin space.
Yeah, it's some abstract space. And it's complex because these coefficients could be complex. This is an abstraction of the functions that we had concrete. So what we showed is that with our concrete functions, we could build an abstract space. Here, we're just ignoring the function part of it and just going right to our abstract space.
Which is a lot easier than trying to figure out what the function for a spin is.
Yeah, of course. I can't write down that function. Never seen it. Okay? So, that's our that's our basis set, up and down. That's all we have. All right? And so now let's build some things. So, for example, the next step is now build some operators. Let me do this. This is, I'm going to specify, these are up and down in a Z basis. Meaning that, you know, it's the picture where this is X, Y, Z, here's S, and then here's MS.
Oh, it's just saying up is positive Z and down is minus Z.
Yeah, and so what I'm doing is I'm saying I'm going to use my Z as a reference.
You're defining.
Yeah, because I'm going to get my S squared with Z. All right? So,
But this spin isn't going to tell you all the information about a particle, it's just going to tell you what spin.
right.
Yeah, so it's very specific to what you're solving.
Yep. We're just doing spin stuff.
Yeah, right, yeah.
Yep. We're going to slap it onto the end of, you know, our goal is to do this. Psi, you know, at hydrogen equals NLML, and now slap on an SMS.
Yeah, that's what I was thinking, yeah, that's what I was
We're
thinking.
just doing the spin part.
Right.
All right, but let's continue with this stuff a little bit. So let's build some operators. Let's build S squared, all right? Okay, so what we know is S squared on up equals, what do we know, the spin? We know the spin is plus h bar over 2. So we know it has to equal h bar squared times the square root of S times S plus 1 times up, right? And then, you know, so when we say h bar squared, so the spin equals plus or minus a half. The h bar is the units of the angular momentum.
If it's squared, wouldn't it just be S times S plus 1, not the square root?
So let's look. So this is going to be h bar squared times a half plus 1 times an up. All right, and what does that equal?
I thought S squared was H bar squared times S plus 1, not the square root. The magnitude of S
Oh,
is
yeah,
the
thank
square
you.
root.
Yep, thank you. Good catch. Good catch. Yep, I'm with you. It's h bar squared, and then what's this? This is 3/2 times a half. So this is 3/4. Okay, so. Yeah? Everybody okay? So now, let's do this. So let me rewrite this. This is S squared up. Alright, so now let me rewrite this as an operator, because I want to find a matrix operator of this thing. Because I know the matrix representation of up and down. So this becomes, let's say it's A, B, C, D times 1, 0 has to equal h bar squared 3 over 4 times 1, 0. Right, I'm building that.
Yep. So it'd be A minus H bar squared times the little 4.
So it's going to be chunk that, right? So it's going to be A times 1 plus B times 0. So this is going to be A, and then this is going to be C. AC has to equal h bar squared 3 over 4 times 1, 0. Right? So what does that make C?
0.
That makes C equal 0. And what does it make A?
1. Or H bar squared.
A equals h bar squared 3 over 4. All right, but it didn't say anything about B and D. All right, so what I'm going to do is I'm going to look at this other case. What do I also know? I also know that s squared on down, what should that give me?
The same thing.
That should give me the same thing.
Okay.
Or s squared times 0, 1 is equal h bar squared 3/4 times 0, 1. All right, should it give you negative though?
Negative. Yeah, because you're minus and
So I was a little bit sloppy over here. I needed a z there. What is the spin of electron? What's the answer? What's the s of an electron?
Spin up or spin down.
1/2.
It's just a number.
No, it's a half. What is the z component of an electron?
The plus or minus.
Plus or minus a half.
So the total spin doesn't really have a sign.
The total spin of an electron is a half. It's the, remember, where does the total spin come from?
So you can do a plus minus and a subscript.
No.
No, because
No, the
remember,
plus or minus is the component.
remember, s equals the square root of the magnitude of s squared, right?
Right.
So it equals the magnitude of s squared.
Because using s squared, we don't have to worry about plus or minus, because anything squared.
So
is
s
equal
of
to
an
plus.
electron equals a half, but sz of an electron equals plus or minus a half. An electron has a spin of a half, that's the answer.
So you don't
But you
divide
can ask, what is the z component of the electron? And then it can either be up or down. Got it?
Yep.
Okay. So here, you're not putting in a minus a half at all, because this is just the spin. What can be minus a half is the ms, right? So s is always a half, the ms can be plus or minus a half. Yeah? Okay, so what does this tell us? Well, we know the same thing. We have AB, CD times 0, 1 has to equal h bar squared 3/4 0, 1. And what you get is d equals 0.
B equals 0.
D equals 0. And,
No, I thought B is 0.
oh, yeah, so hold on 1 second. Oh, yeah, I use different letters in the book, okay? So I was just going to cheat and use the book, but I have to figure this out. So then it's A times B. So this says that,
Yeah, BD instead of AC.
oh, no, it's
Yeah,
B.
B is 1.
B has to equal 0,
And D equals h bar squared 3/4.
and then D equals h bar squared 3/4. All right, so what have I just done?
If you have replaced A, B, C, D with
So check it out. So now my operator in matrix form
for S
for
squared.
s squared equals, you ready? It equals, I'll do it like this, 3/4 h bar squared 1, 0, 0, 1. Okay, now, what I'd like to do is, and it will seem like it doesn't matter right now, but what I sometimes do is I do something like this, in a z basis. I put a little bit here. Because I built this in what original basis? In a basis of up and down in the z direction.
So we have to put the subscript in the Z of 9.
Right, so, because look, someone else could have chose the x direction or the y direction, so they could have built it in a completely different basis. All right, but this is what it looks like in our z basis. All right. Can you build an SZ?